honestly does exactly what it says, it differentiates. So I'm gonna draw a circuit with resistor labeled RF, and this is a capacitor labeled C. And so as you can see, I have an input voltage of Vin and an output voltage of Vout. And I should also note this is in time domain. And so what we want to do is we have a problem. And so given the circuit below, we're going to first find Vout, and then we're going to find the transfer function, so essentially Vout over Vin. And with that, we're going to sketch the frequency response of the circuit, assuming, so we want to assume no energy stored. So what does this mean? No initial conditions. Makes our lives so much easier with that. So what are we gonna do? We're gonna find, how are we gonna do this? With nodal analysis. So if you recall the rules of op amps, this current here is equal to 0, and the same for these two over here. So the current going into the op amp and out of the op amp has to be 0. So that means this Vi, the nodal voltage at the inverting terminal, is equal to the nodal voltage at the non-inverting terminal. So that equals 0. But for our terms, we're just going to label this as Vx equals 0. Because since they're the same thing, we're just going to call it Vx. We also want to label this current to resistor as I. And so if no current can be going into the op amp, that means that all the current has to be going through the capacitor and then through the resistor. And this is for an ideal. So with this, we just simply solve as we would any other op amp problem. So here, we know IC. Also, we know that IC. This is just one of the definitions of a capacitor, in that the the current through a capacitor is equal to the capacitance times the derivative of the voltage through the capacitor. So we also know minus V out. Essentially Ohm's law. Kind of. We just know that since this is equal to 0, all the current has to be going from V out to this Vin, which is equal to 0, and it goes through this resistor RF. And then, so let's just rewrite our equation as C through dt equal to 0 minus V out. So simplifying this a little bit more, C, because Vn, the voltage in, is also the voltage through the capacitor, over d2 negative V out. Now we just rearrange and we get V out to negative RF C over dt. And that's our V out. And so for B, so we find the transfer function. we're going to do this a little differently. We're going to instead convert this circuit into the Laplace domain, or the frequency domain. So it's going to look actually really similar. So since we know that there was no initial energy stored, we know that there's no input voltage or output voltage here. That would be defined as something. We just know that since it's no initial conditions, there's no voltage source right next to the capacitor. So this is going to be 1 over SC, regular op amp. This is still remains RF because resistors, simply resistors. See to me. So this is quite simple, just like how you would do any kind of op amp in the frequency domain. You would treat this as an impedance and treat this as an impedance. And so we define out is equal to negative this impedance, negative RF, here, SC. So it would be rearrange this so that it's V out over V in, have negative RF, C, S. Here is our transfer function. Now we can also see how similar these two equations are. This is essentially the Laplace form of V out in the time domain. That's essentially what this is. It makes it really easy if you recall that the Laplace derivative is equal to S f of S minus f of 0. And since we had no initial conditions, this is 0. And so that's where we got this S from here. Okay, now for the final part of our problem, where we sketch frequency response. For the circuit. So here we're just gonna do, note how it says sketch. We don't have log papers, so we're not really gonna worry about that. And so we have H of S equals -4. So this is quite easily like the most simple buddy plot you could have, with this being the K component. So let's do a rough sketch K component. For the absolute value of negative RF. So it's just 20 log base 10 of RFC. We're going to say this is, and it's just a flat line. And so as for our 0 component, making this blue, we know that it's just a line through the point omega equals 1 with a slope of 20 decibels per second. And so since this graph is kind of just a rough sketch, I'm not really going to worry about making sure that it's exactly rise over run 20. We're just going to have, here's the intercept to 1, and the decibels per decade. For that confusion, we're just going to do the final, where it intersects here, and it goes up 20 decibels per decade. Yeah, here we go. That's just the very rough sketch of the frequency response of the circuit, and it just gives you some idea of a differentiating op amp. But honestly, that's all there is. It's pretty simple. Thank you very much. Like and subscribe.